All right, anytime you are approaching a proof, always begin with the given. So again, this first step should be the same for everybody. Do notice I combined these two statements into one. A is the midpoint of both wy and zx. Now you can do that, but don't reinterpret the given information. Just make sure you write it as the whatever statement they provide. Okay. All right, so after you copy down the initial state, the given information, do one of two things. Either introduce elements from the end state or interpret the given information. Okay, either one of those is fine right here. This first statement, wy and zx are equal. There's not a whole lot to interpret from that, so we don't need to do anything from that, or even there's not a whole lot of information to build from that. But the next one we can interpret, right? The statement A is the midpoint, that needs to be converted into a measurement that we can use. So if A is the midpoint of wy, what does that tell us? What information is provided by that statement? So what is the relationship between the pieces? Okay, so now we will get to that in a second, but as far as just being the midpoint, by definition of a midpoint does what to a segment? Okay, bisects it, cuts it into two equal parts. So what do you know about these segments here? WA and AY are equal. And we know that by definition of midpoint. Okay, so that is how we define midpoint, cuts the segment into two equal parts. So in doing this, we also happen to introduce this element too, right? We introduced one of our end state elements that hadn't been in our proof yet. So we actually accomplished both things that I would say would be your next step. Okay, at the same time, we have another statement about a midpoint. So what other statement can we write in the same step two? ZA and AX also have to be equal. All right, so there's the two pieces of information that we can start with.
WA plus AY equals WY.
Okay, so WA plus AY is equal to WY. And so that's segment addition. Remember, we don't really have a whole lot of justifications yet, just our postulates, axioms, and definitions. Okay, so segment addition is a good way. It allows us to introduce WA. It also ties it to a relationship that's already in the proof, right, the WY. Okay, using the same logic, what other statement could we introduce in this same step? ZA and AX are the sum of the parts for the whole ZX. And so that's also a segment addition. And now the reason why that might be useful is, what do we know is true about these two relationships? If those are the same, what do we know about the expressions that contain them? They're also the same, right? So if we were to substitute that in WA plus AY, okay, so we know that we can substitute this sum of terms in for WY, and at the same time we can substitute ZA plus AX in for ZX up here. So really we're taking this statement right here, converting it to the equality form, and substituting in equivalent values. So what would justify this statement? Anytime you replace something, we call that the substitution property. Right, so what we now have, and what this has allowed us to do, again, is we're building closer and closer to our end state. We now have WA and ZA on opposite sides of the equation. And so we're almost done with what we want to accomplish here. Any ideas on where we could go next? Okay, we need to get rid of AY and AX, right? Somehow. Well, what do we know that AY is equivalent to? It is equivalent to WA, right? So what if we make that substitution here? WA plus WA, so we're just replacing this with its equivalent, and that's equal to ZA plus, well, also we want to get rid of AX. AX is equivalent to ZA also. So what did we do here? We replaced again, so we substituted. Now, could we combine these into the same step? No, and the reason for that is statement 5 is actually built on statement 4. So you have to have statement 4 in by itself, and then you can build up to statement 5. Okay, and when we do that, this leads to our next statement. If we just simplified the equation in step 5, what would we get? When you add WA plus WA, that's equal to 2WA. And when you add ZA and ZA, 2ZA. Now, here's one of the things that you need to be able to distinguish, and it's very subtle, but hopefully you can see how it's different. Okay, this is not an example of the addition property. Okay, so remember, the addition property was based on the concept of you add the same value to both sides of an equation, so you're taking a value that wasn't there to start with and you're adding it to both sides of the equation. And that remains, the sums remain the same. In this one, did we add something that wasn't already there? No, all we did was we manipulated the things that were, right? We combined like terms. If you are combining like terms or simplifying on the same side of an equation, so you're not actually doing the same operation to both sides, when you identify it, call it just by the operation that's being performed. So this isn't addition property, it's just addition. And all we did is we combined our like terms. And so you could explain it in terms of words. If you're doing things where you're combining like terms and multiplying or distributing, explain what you did. If you're doing a whole bunch of different things all in the same step, you can just use the justification simplify and simplify it algebraically. But if you can, identify it as a single individual mathematical operation. So we added. And now what can we do to both sides to finish this proof? In order to reach our end state, we need to divide each side by 2. So we get WA is equal to ZA. Now, did we do the same thing to both sides of the equation? Yeah, so now this is going to be division property, right? If we had just simplified it, the individual sides of the equation, completely irrespective of the other side, then it would just be division. But here we did the same thing to both sides. And now, the last kind of subtle thing is our end state written exactly like the proof that we're trying to complete? No. Here we have a relationship of measurements, and here we have a relationship of geometric figures. Can we convert from one to the other? Can we state that since these distances are the same, the segments that contain those distances have to be congruent, right? And the justification for that is going to be definition of congruence. Remember, congruence means equal in all respect. It also allows you to justify using the common notion that if things coincide, there are things that coincide are equal to each other.